I'm Jeremy Jorgensen at Brigham Young University and going to be talking about what an introduction to structural equation modeling, what these models are and how to set them up. So why would we want to use structural equation modeling? This tool is actually an advanced tool that combines regression and factor analysis in one single step. And the regression part of a model is shown with regression paths, while the factor analysis is shown in a measurement portion of a model. I'll talk about those and give some examples in a few minutes. By adding factor analysis to regression, we're able to include measurement error in our model to take that into account. And so essentially we're getting a little more accurate of a picture of what our data are showing. Some might ask, why not just use regular regression? Like why learn a different technique? Why learn all these different things when you could essentially run the same analysis within regression? And one of the main benefits of SEM is that within a regular regression framework, when you have a measure that is composed of multiple items, and let's say you add those together into a scale variable, you assume equal weight for those variables, for the individual items, that they all play the same role in that scale, or they have the same weight in that scale. And that may not be the case. Now, if you have high alpha reliability for a number of items on a scale, then the difference that you're going to find between SEM and regression is going to be much smaller. In fact, you may not find any difference at all. However, if you don't have as high of reliability, then an SEM framework may be a better approach to take. And we take into account measurement error. So those are two reasons why SEM might be a good way to go. So the difference might look something like this. From a regression framework, we have a single variable of how much time you study predicting test scores for students. And we could run this in a regular regression framework and get a good answer. From an SEM framework, it may be that the number of hours studied plays less of a role than, say, effective study habits or studying in a group. And it might also be that test scores fluctuate across classes or across a semester. And so we might be able to actually model something that more accurately portrays reality within an SEM framework than just using a regular regression framework. Now, I want to introduce the term measurement and structural portion of the models. You see here a single oval here of study time. This is a latent variable with 3 indicators, and those each have error terms. And this makes up a confirmatory factor analysis or a measurement portion of the model indicating study time. And over here we have the measurement portion indicating test scores. The regression between those is what we refer to as a structural portion of the model. And so when you see that in the literature, a lot of times people will say, well, I ran a measurement model and then I ran a structural model. And this is what we're referring to. And I'll talk about this a little bit more here in a few minutes. So the measurement model is usually a preliminary model. And oftentimes you see here in this example that I have a covariance going between the variables. Nice. I'm just going to not take that call right now and turn down the volume. Okay. So I'll just start over with this slide. Is that okay? So in a measurement model, we have oftentimes covariances between a latent variable let's say health is a predictor here, and attachment to parents is another predictor, and marital satisfaction is the outcome. Instead of having a regression path between these, we might want to have a covariance between these. And this model right here is the one that I would take correlations between my latent variables and other variables and create a correlation table that I would report in my manuscript. And we could call that, like the title of that table might be latent variable correlations from the measurement model. And we might also report from that model the factor loadings for the confirmatory factor analysis portion of the model. As a next step, we would pull out those covariance paths or covariance parameters and add in a regression like we see here with the structural model. And so we could talk about our measurement model, say in a manuscript, followed by the structural model, where the regression paths oftentimes are testing our hypotheses. Okay, it's important to remember that although we're using an arrow that points from an X to a Y, or from a predictor to an outcome variable, the statistical procedures involved in SEM are based on correlations. And so it's important to not assume causality, even though it appears that that's what we're modeling. Oftentimes, especially with more complex models, there are many different ways that we could configure a model or estimate a model. And so it's important that we have a theoretically grounded model. That's rule number one, to never put anything in a model that we don't have some theory for including. It's also good to have parsimony in our models. If we simply connect everything in our model to everything else, then oftentimes we have what's called a saturated model, which may be overspecified. We may just have too much in there. And so it's good to theoretically have a concise model, an efficient model. Those increase degrees of freedom and maybe a more appropriate representation of what the data show. We also want our model to fit the data that we have. We'll talk about that in a different lecture on model fit. So what is a variance-covariance matrix? I'm not going to get into the details of this right now, but if you think about a correlation matrix where on the diagonal usually you have ones, let's say on the y-axis you have the names of the variables, and then on the x-axis you have those names repeated. So when the first variable x1 is correlated with x1, you get a 1, and you have ones all the way down on the diagonal. And then on the off diagonal, you have the correlations between 1 and 2, and 1 and 3, and 2 and 3, and 2 and 4, and so forth. In a variance-covariance matrix, the diagonal, instead of being made up of ones, is made up of variances. So if we take the variance of variable number 1, we would put that there. And the variance of number 2 would be the next number down on the diagonal. And the variance of variable number 3 would be the next number down. And then the covariances would be the covariance, or the unstandardized correlation, of variables 1 and 2. So on the diagonal, you have two variances, say between variables 1 and 2, and then on the off diagonal, we have the covariance between 1 and 2. And it becomes important to understand what a variance-covariance matrix is, because we're going to work with those here later on when we're learning more about how much information is going into a structural equation model, how many parameters we're asking out, and is that an appropriate amount. So look up variance-covariance matrix, try and understand what those are, and in later lectures we're going to learn more about that. In structural equation modeling, we have a few different types of variables. The main types are either latent variables that are usually represented by round circles or ovals in SEM software or in diagrams. And then we have observed variables that are usually square or rectangular. And the latent variables, or the round ones, are hypothetical. They're not in your data set. They're something that we're creating with our SEM model. And the error terms, which you'll learn more about, or residuals, are a type of latent variable. And these are attached to any variable that's an outcome in the model. Not predictors, just outcomes, unless sometimes you have a variable that's a predictor and an outcome in a model, in which case it would have an error term. Observed variables, or the ones that are measured in your data set, are sometimes called manifest variables, or if they're part of a measurement model, if they're part of a confirmatory factor analysis, then they are usually indicators of a latent variable. We sometimes talk about them that way. Let's see here. So in a model, we have variances of variables that are estimated, and we also have means that can be estimated. Let's see, I think I might be covering too much in this little bullet point. Let me say this. So on a latent variable, let's say we have 4 indicators that are part of a latent variable. If those indicators follow different scales, like one of them is 1 to 5, and one is 1 to 3, and one is 1 to 15, or 1 to 20, then if we estimate the mean and the variance of a latent variable, that those are all indicators for, the mean of that latent variable doesn't really correspond to any one of the individual items. It is a composite for all of them. Now, if they're all following the same scale, like they're all 1 to 3, then our mean on our latent variable does make contextual sense, because it would represent essentially the mean of all of those variables put together. I'll talk about a little bit more about what those mean here later. Okay, structural equation modeling is a large sample technique. So in a regression model where we're not using SEM, we could have a sample of 10 or 15 or 20 people, and a model would likely still run. However, in structural equation modeling, we like to have, for every observed variable in our model, we like to have at least 10 people in our sample. And so given that most models are going to have 10 or more variables in it, you're going to likely need 100 or more people in your sample to estimate a structural equation model. There is a rule out there called the N to Q rule, and this is the sample size is represented by N, and Q represents the number of parameters. And so if we're estimating, for every parameter we're estimating, this rule suggests that we have 10 people in the sample. And that's a good rule to follow. A quick count rule would be to count how many observed variables or squares or rectangles you have in your model, and then multiply that by 10, and that's how much sample size you would need. What happens if you don't have enough people in your sample? Well, first of all, you might have less trust in your results. But second of all, you might get this nasty message from the program saying that there's a negative variance in your model, and that can't be estimated, and so it actually is telling you that the model is not running. And that may be just a decoy warning, when really what's going on is that your sample size is not large enough for the model you're trying to estimate. So when we're comparing our sample size to the number of parameters we're estimating, we would want to count up the number of variances, covariances, regressions, and sometimes means. And when we subtract those from the amount of information that we're putting into the model, the variances and covariances of the model from a covariance matrix, then we would get degrees of freedom. And you need to have at least 0 degrees of freedom, not negative degrees of freedom, for your model to run. Preferably, you have positive degrees of freedom. And I will get more into this issue of is our model what's called identified or not in a different lecture. So for now, I'm just going to introduce that idea and let that start to sink in a little bit. Okay, so what is more important when we are using statistics? Is it more important that we find statistical significance, or that the effect size of, say, X predicting Y is, I don't know, of a significant level, or if it's large enough to mean something meaningful? You might say, well, it's important to have something meaningful, right? Yes, I agree with that. So statistical significance, at the same time, it's very difficult to publish papers that have no statistical significance. So that might be a necessary but not sufficient rule for what we're looking for. Klein offers a caution in his book. He says that most, if not most, published reports of the application of SEM have at least one flaw so serious that it compromises the scientific value of the article. That gives you a lot of trust in the research that's published with this technique. I would probably not be so pessimistic about it and say, you know, most papers have something of value that they published. They might have errors. But I think we do need to be important and take this caution into account and say, okay, let's make sure we do this right. Let's take all the appropriate steps and make sure that we have the right information in a manuscript and do the models appropriately. SEM has been called a disconfirmatory approach. So our model fit helps us to know that our model fits our data appropriately. But really, that's not necessarily saying that the model is a good model. It's just saying that it's not a bad model. And so having model fit doesn't actually tell us if the model fits reality or if that's really how life is. So we have to use theory to back up any models that we have. There are a number of software packages that we can use to estimate structural equation models. I'll use some examples here in AMOS and M+. Stata has a new platform out that will allow you to use SEM within Stata. They have a diagramming or a syntax-based platform that you could use. Lizerl is, I believe, the oldest SEM software. I'm not 100% sure on that, but that's the one I've heard about for the most years. And it's based solely on matrices. SAS has a SEM component. EQS and R is a famous one as well. So I'd like to show a couple of examples in AMOS and M+. So I'm going to start with AMOS, and my goal here is to help you understand what these components mean in an SEM framework. And I've started here with what I'm calling a one-variable model. Okay, this is a measure of togetherness in marriage from a data set that I've used. Okay, so I'm going to, whoops, I pushed the wrong thing. I'm going to go ahead and estimate this model. And it looks like it ran, so now I'm going to go to the output and see what my output is. And the main thing that I want to look at here is I want to determine what is the mean and the variance of togetherness. Okay? And so if I get this model here, it says here minimum was achieved. That tells me that my model ran. I do have 0 degrees of freedom, so it's not going to give me model fit indices. But if I scroll down here, I see that under means, I have a mean of 4.764 and a variance of 0.425. Okay, so 4.764 with a variance of 0.425. Okay, and now I'm going to add to this model an error term. And we're going to see what does it mean when you have an error term for a one variable model. And I've got to name that error term, so I'm going to do name unobserved variables, and then I'm going to run it again. And I'm going to look at the output here, and let's see here. I still have 0 degrees of freedom. The minimum was achieved, so the model ran. And if I scroll down here, we now have, instead of a mean, we have an intercept. Now, in SEM, a lot of times we talk about means and intercepts. And in fact, if we have missing data, we will estimate means and intercepts. And when we're doing that, usually we talk about means as the average for the sample in the predictor variables and the intercepts as the average for the sample for the outcome variables. And notice that we do not have a standard deviation anymore, but rather we have a variance for the error term. And our intercept for together one is 4.764. That's the same as the mean before, right? And then the variance of E1 of that error term is 0.425, which is the same as the standard deviation of the variable without an error term. So the variance of the error without anything else in the model simply represents the variance in the variable, or the standard deviation of the variable. Let's see here. Now, let's see, I want to make sure I'm talking about this correctly. Let me just run that one more time without this. Okay, so I said standard deviation. It's actually the variance. And so we have a mean and a variance. And so the error variance is the same as the variable variance. And the way you calculate the variance is by squaring the standard deviation. So we could take the square root of 0.425, and that would give us the standard deviation of togetherness. Okay, I just wanted to make sure I was using the right terms. Now, you'll notice when I put an error term on here that a little 0 shows up there. And that's because we have missing data in this model. And so under analysis properties, we have clicked on this box that says estimate means and intercepts. Okay, and so the mean of this residual is constrained to be 0. Okay, I wanted to show one other little thing here. So let's say, let me pull out another variable here, together at time 2 from this data set. And I'm going to correlate these two variables with this two-headed arrow. I'm just going to click and drag over to the second variable. Then I'm going to run this. And for my output, I am going to get here, looks like minimum was achieved, so it ran. We still have 0 degrees of freedom. And we have means for these two variables, 4.757, 4.259. We have a covariance, which is the unstandardized correlation, and then we have the correlation, which is the standardized covariance. So these are correlated, 0.396 or 0.40, and then we have variances for these two variables. Now, remember, 0.396 was the covariance, or excuse me, the correlation. So we could take off this correlation, add two error terms, and correlate those. I'm going to have to name those two errors and then run it. And we should get, actually, minimum was achieved, 0 degrees of freedom. We should get the same information. So the intercepts now, together one, look like the means from before. The covariance or correlation is exactly the same between the two. And here we have the variances of the error terms rather than the variances of the regular variables. Okay, so there are a few other ways we could estimate this model. I'm not going to do all those, but I want to point out, let's see, one other thing. Let's run one more model, or a couple more. Let's see, the correlation, the standardized correlation between these two variables was 0.396, right? Okay, so let's take and put a regression path between these two and throw an error term. I guess I should have kept that one there, and we'll name that, and then run this. And we have 0 degrees of freedom. Once again, minimum was achieved. Now we have a regression weight. This is the unstandardized regression weight of 0.624. Here is the standardized regression weight. Look at that, 0.396. That's the same as the correlation from the last model. And so it's important to understand that when we're looking at regression paths, a standardized regression path should be the same number as a standardized correlation between two variables. And in an SEM framework, if we're modeling error terms, it essentially means the same thing. To correlate two errors is the same thing as correlating two variables. Okay. Very good. That's all I'm going to do there. Now, if we were to move to M+, we would have a one variable model. Looks like this. So this is the same data set. I've got together 1 and together 2. I've called them TOG1 and TOG2. And the model, if we just run it with one variable here, go ahead and run that. We've got a couple of warnings. It says all variables are uncorrelated with all other variables in the model. Okay, so there's nothing correlated with anybody else. And then we've got a few cases with missing on all variables. So that bumps us down to 175 cases. And if we scroll down, we have 2 parameters that we're estimating with 0 degrees of freedom. So, and then if we come down here on our model results, we see the mean of TOG1 is 4.764. That's about the same, maybe that is exactly the same as the one we saw in Amos. And then the variance 0.425, that is the same number that we saw in Amos. If we go to standardized, we get a little different numbers, but that standardizes the variance on a scale of 0 to 1. Okay, so let's go back to our input. And because M+ assumes error terms, you'd have to do some different things to actually plug an error term in there. Actually, let me look at one more thing here. So if I were to run this, M+ now has this new feature called View Diagram. So if we just click on View Diagram, this is going to show us what our model looks like. And there it is. It's a one variable model, and here's the variance, and this is probably the standard error of the variance. Okay? So we could then take add with TOG2 and use variables TOG1, TOG2. And here we have fewer missing now. We're now estimating 5 parameters, still with 0 degrees of freedom on that chi-square. And scrolling down here, TOG1 with TOG2, this is unstandardized, 0.266. We've got these 2 means and the 2 variances. We've seen these before, haven't we? And then we have the correlation, 0.396. So that's what we saw over in Amos. Let's see. We could alternatively model this as TOG2 on TOG1, which is a regression. And we're asking for standardized variables, standardized in our output. Here we've got some missing now on predictors, missing on outcomes. And okay, scrolling down here, we see that we have an unstandardized regression of 0.622 with an intercept of 1.33, a residual variance of 0.89, moving down to our standardized regression, 0.40. It looks like it got bumped up a little bit from what we saw in Amos, but that's essentially the same as the correlation between the two. So I will go over latent variables, how to create those, doing some preliminary analyses with factor analysis in another lecture. I hope you consider structural equation modeling as an appropriate tool when you have large samples, when you're using measures that have multiple items that perhaps don't have great reliability, or no, I would say excellent reliability. Something less than that, you might benefit from SEM. And it could be a good tool that could be helpful for you in trying to understand answers to your research questions. All right, thank you very much.